Hello. So today we're going to be talking about mole conversion, specifically focusing on Avogadros, where we're converting moles to molecules or moles to atoms, moles to any particles, or the reverse. So when we have a mathematical representation showing how things work, we oftentimes use a balanced chemical reaction to compare things. So for this one, we can compare the 2 moles of water to 2 moles of hydrogen gas and 1 mole of oxygen gas. And so later on, you'll learn about that with the mole ratio. But moles can be compared mathematically using the balanced chemical reaction to do that. So what does that mean exactly? If I have, does not matter, 5 moles of a product, so I was able to produce 5 moles of hydrogen gas at 100% yield, so that we're assuming perfect conditions. That means that I would have only 2.5 moles of oxygen gas, because we're always going to produce double the hydrogen gas to the oxygen gas. So any of these mole relationships you can work through just by using that logic of comparing each other one. That's one way mathematically to relate the moles of different things. Now, atoms and molecules are too small to count usually, which is why in the chemical reactions, we're going to just use that word moles to do that representation. And a mole is a whole lot of atoms and molecules. Okay, so even though moles is a made-up number, it can be used to calculate things. So the atoms are chemically combined into molecules. So if we have a lone hydrogen, which we don't usually have, and a lone oxygen, if we had 2 hydrogens and 1 oxygen, we could make water. Now we know that's not how it exists in real life because of the diatomic nature of those guys, but we can still show how those ratios are working. And this guy is a covalent bond. How do we know that? All nonmetals. And so he would actually be use prefixes to name him, dihydrogen monoxide, to make that chemical bond. And the Avogadro's number, again, is going to help us relate it, but it only works for the base units. So if we have so many atoms of hydrogen, then we can use Avogadro's number directly. If we have so many molecules of hydrogen gas, actually, then we could use this guy. You have to be really careful. If it is just a single element, neon atoms, then you can use Avogadro's directly. Okay. Hydrogen gas gives you molecules when you use Avogadro's number. After that, you have to use a relationship. So let's look at water. Water is 2 hydrogens and 1 oxygen. So if I figure out the molecules of water, that's equal to 2 hydrogens and 1 oxygen, same as what we did before to find valence electrons, same as what we did before to find a molar mass. But that also is going to give us a relationship. 2 plus 1 is 3 atoms. So for every 1 molecule of water, there are 3 atoms. So sometimes you have to do another further thing. For instance, if they asked us for how many atoms are in 10 moles of water. Atoms is not the base unit for molecules. Molecules is. All right, so let's try some basic ones and then we'll work up to that higher level one that I'm discussing. Every single time, known equals question mark unknown. What do we know? We have 30.0 moles of carbon dioxide, and that's equal to what's our unknown, what we're trying to find, molecules. Now, this is not stoichiometry. We're converting from the same chemical to the same chemical. So these would be called mole conversions. These mole conversions would use Avogadro's number. Not all conversions use Avogadro's, just when we're dealing with what? Particles, exactly. So our pathway for this one is to go from moles to molecules. From moles to molecules. We already have moles at the start, so we know we just have 1 unit conversion. our setup of our equation, known over 1, and then we're going from moles to molecules. The from always goes on the bottom, and the to goes on the top. The known always goes on the bottom, and the unknown always goes on the top. And then we can substitute in. What's our known? 30.0 moles of carbon dioxide. This over here is a fraction that's called a unit conversion because we're converting from one set of units to other. We're converting from moles to molecules. And the unit conversion, like I said, we're going to use is Avogadro's, where 1 mole is 6.02 times 10 to the 23rd molecules. And then we can cancel. Moles of carbon dioxide cancels with the moles, and we end up with molecules of carbon dioxide. And then I just look back, is that what my unknown says? Phew, I have the setup correct. So now I can go to my calculator. 30 over 1 times 6.02 times 10 to the 23rd over 1 is going to give me, and you can always do it in your calculator. I recommend it to make sure you're using your calculator properly, because sometimes the calculator will mess up your PEMDAS if you're not inputting it the way it particularly likes. 1.806 times 10 to the 25th molecules of carbon dioxide. Substitute, solve, sig figs. The 3 is significant, and I have a decimal place, which means the trailing zeros are significant. I need to round my answer to 3 sig figs. Underline the first 3 significants. Why did I underline that 0? It's a contained 0. It's trapped between 2 non-zeros, so it is significant. So that leaves my place to round to at the hundredths. So now switch to your math brain and round to the nearest hundredth. That would be rounding down to 1.80 times 10 to the 25th, or rounding up to 1.81 times 10 to the 25th. How do I know? Look at my next number, he's a 6. So we are going to round up in this case. Now notice when we did this, did I have to know it was carbon dioxide? I did not. It didn't have to be a gas. It did not have to be a molecule. It had to be a molecule because it's carbon dioxide. But it could be any molecule. Hydrogen gas would have given me the same answer. 30 moles of hydrogen gas is 1.81 times 10 to the 25th molecules of hydrogen gas. Diphosphorus pentoxide, 30 moles of P2O5 would give me 1.81 times 10 to the 25th molecules of P2O5. The actual identity did not matter except for knowing that the base unit has to be molecules. And just remember, moles are not molecules. Moles are not molecules. Keep telling that to yourself if you're still struggling with that. All right, how many atoms in 30.0 moles of carbon-14? 30.0 moles of carbon-14, or you could write it carbon-14, and that's its chemical formula makeup. Because we write the 14 is the mass, so that goes in that superscript area. Is equal to how many atoms? So in this case, we are going from moles to atoms of the same structure. They're both carbon-14. So we know we see moles at the beginning. So we're just going to have one unit conversion because carbon-14 is an element. It's an isotope. Yep, it's carbon-14 instead of carbon-12, but it still works the same way. If you're not involving mass into the equation, then it does not matter what the mass of carbon is, whether it's the one that's on the periodic table or a different one. Known over 1 is how we start. One unit conversion is going to go from moles to atoms. The froms go on the bottom because we're dividing out the moles. The atoms go on the top because we're multiplying in the atoms. Okay, what is our known? We just replace that whole thing, 30.0 moles of C14. And this is moles to atoms. Again, the double check. I can use Avogadro's here. 1 mole is equal to 6.02 times 10 to the 23rd atoms of C14. Why? The base unit of carbon-14 is an atom because carbon-14 is an element. Anytime you see an element, its base unit is an atom. Moles cancels, and we're left with atoms, which is what I wanted. So got this set up right, plug it in the calculator, and lo and behold, it is the same thing as the last slide. Why is that? Because we're only working with those base units. We still had the same unit conversion. So we have the same exact setup as before. Atoms are what's in 1 mole of elements. Okay, so a little bit further detail on how that works. Let's do another one. How many atoms in 30.0 moles of carbon dioxide? This is where some alarm should be going off right there. Wait, atoms is not a base unit of carbon monoxide. Carbon monoxide, not a base unit. We cannot use it that way. All right, this is a molecule of carbon monoxide. So we're going to need an additional conversion. So let's still do known equals question mark unknown. 30 moles of carbon monoxide is equal to how many atoms? But our conversion, it has to be moles to molecules and then molecules to atoms. So we have 2 unit conversions here. Known over 1, and then remember from's on the bottom, 2's on the top. Okay, so you can rewrite the whole thing that way. Our known is going to be what? 30.0 moles of carbon monoxide. And we're going to now have to get rid of that. So our first unit conversion is going from moles to molecules, from moles to molecules. And our second unit conversion is going from molecules to atoms, from molecules to atoms. It has to be in this arrangement. If it was any other arrangement, the moles wouldn't cancel and the molecules wouldn't cancel. So you'd end up with molecules squared or moles squared or something like this. But here, by doing that unit conversion, we end up with atoms. So we can go, okay, we're on the right track. 1 mole is equal to 6.02 times 10 to the 23rd. I can use Avogadro's here because that is the base unit. Carbon monoxide is a molecule, so 1 mole is equal to 6.02 times 10 to the 23rd molecules. And then we have that next step. We have in 1 molecule, there is 2 atoms. So we're going to take 1 more conversion here and multiply by 2. So the only difference in this one, again, is if you are not at your base unit, you have an additional unit conversion. 1 molecule equals X atoms, which you can get from the chemical formula. There is our answer, 3.61 times 10 to the 25th atoms of carbon dioxide. Anytime you're dealing with particles, whether that be formula units, atoms, molecules, you are going to have typically a very large number. So always check in your calculator that you see something. Now your calculator might go 3.61 e to the 25th. And sometimes it's like 3.605725, and you start to kind of zone out right there. Make sure you're always checking. If there's an e at the end, that just means times 10 to the. So make sure you are aware. Anytime you see particles, check around for that exponent. Check always, but especially check what particles. All right, how many moles? Okay, so we're going to go to moles this time. In 10.0 times 10 to the 24 molecules of who? Carbon monoxide. So in this case, we're going the other direction. We're going from molecules to moles. Carbon dioxide and carbon monoxide and hydrogen gas. Molecules is the base unit. So we are only going directly from molecules to moles. We do not need to do another step in there. We can just use Avogadro's to go from molecules of a molecule to moles of that substance. Known over 1, 10.0 times 10 to the 24 molecules of carbon monoxide times 1 unit conversion, because we have 1 arrow, which goes where? What is Avogadro's number? Avogadro's number is 1 mole is equal to 6.02 times 10 to the 23rd molecules. Match up your units. We're going from molecules to moles. The moles is attached to the 1. The molecules is attached to the 6.02 times 10 to the 23rd. Okay, so in this case, to get the units to cancel, we had to divide by molecules. Anytime you start with molecules, you're going to be dividing by the Avogadro's number because we have to get rid of the molecules to convert it to moles. This one especially you might want to do with me because whenever you're dividing exponents on a calculator, sometimes the calculator gets confused. And so when I plug that in, 16.611295 and so on, and I look and there's no E at the end. Does that make sense? Yeah, because we're going from molecules to moles. So oftentimes we will not have an exponent. Not always, but oftentimes. How many sig figs? 1, 2, 3. You don't count sig figs after the x. That 10 to the 24th is important for a placeholder because it's actually a positive exponent. So it's a really, really, really large number. But in terms of sig figs, we only look at before the x. I have 3 sig figs. So I underline the first 3. We're going to round to the nearest 10th in this case, or the first decimal place. So it's either going to round down to 16.6 moles of carbon monoxide, or it's going to round up to 16.7 moles of carbon monoxide. How do we know? We look at the next number. It's a 1. So we're going to round down in this case. How much volume in 10.0 times 10 to the 24th molecules of carbon monoxide? The known goes on the left side, the unknown goes in the right side. How did I know liters for volume? Typically, we will use milliliters, liters, decimeters cubed, centimeters cubed, and sometimes we use the medical cc's. But when I'm doing mole conversions, my base unit is liters. So unless they tell you otherwise, you're going to use liters for year 1 chemistry when they ask you for the volume of something and you're doing a conversion. Now, when I look at this, there's some added words, gas at STP. Now, at the start of the year, we probably ignored that, but now we know STP is standard temperature and pressure, 0 degrees and 1 atmosphere. Do I have to incorporate that? At this point, you do not need to, but you do have to recognize 1 mole equals 22.4 liters is only for gases at STP. So if this was a solid, you could not use that conversion. If this was not at 0 degrees C and 1 atmosphere, you could not use it. So this is only used in special situations, but thankfully it is in this particular situation. We are going from molecules to liters. What didn't I talk about? Moles. Moles is that thing that lets you do those conversions. It's that imaginary number. So if you don't see it say moles at the start and you don't see it say moles at the end, it's going to be somewhere in the middle. I'm going to convert from molecules to moles. Let me double check. Carbon monoxide is a molecule, so I can use Avogadro's number directly. And then I'm going to go from moles to liters. So I have 2 unit conversions I'm going to need, and I have 2 arrows. So I have 2 from 2's, from on the bottom to get rid of the old, divide out the old, multiply in the new. All right, what is our known? 10.0 times 10 to the 24th molecules of carbon monoxide. Just took it directly off our known statement. We are going for our first arrow from molecules to moles, from molecules to moles. And our second arrow is going from moles to liters, from moles to liters. So I'm just replacing the from to with the units. Start with only the units so that you don't accidentally mix up what the unit conversion is and then go back. For this first unit conversion, I'm using molecules and moles. So that's this first guy. It doesn't matter if my unit conversion says 1 mole equals 6.02 times 10 to the 23rd molecules, or 6.02 times 10 to the 23rd molecules equals 1 mole, because it can be arranged in either way. Which direction do we need it now? The 6.02 times 10 to the 23rd is with molecules, so that is going to go on the denominator this time, and the 1 is going to go on the numerator. How about the next guy? This one's comparing molar volumes. The 1 goes with the mole and the 22.4 goes with the liters. So now we have this setup. Again, you might want to pause and double check that you are getting the same answer. Because anytime we're dealing with exponents, you want to make sure you're comfortable with your particular calculator. The SOL this year is supposed to allow you to use Desmos. So we will see how well that works out. Hopefully it does work out well. 372.09302, and then it keeps going on. But I know what, I only have 3 significant numbers here, so I'm not going to need that many. 1, 2, 3. Round to the nearest whole number in this case, or it could say 0 decimal places or round to the nearest ones. This place has a lot of different things, but it still all works the same. I'm either going to round down to 372 or round up to 373. And in this case, 372 liters is going to be my answer of carbon monoxide. Notice, did I need to know what the chemical was? Nope, it could be carbon dioxide, it could be hydrogen gas. As long as it was a gas at STP, this formula would yield the same results. How much mass in 10.0 molecules of carbon dioxide at STP? So we see the STP right there, which means we can use molar volume if we need it. But start with what you know. What do we know? 10.0 times 10 to the 24th molecules of carbon dioxide is equal to how much mass? Mass doesn't have units of liters. Mass has units of grams. So here we're going from molecules to grams. Can we go there directly? No. Molecules of carbon dioxide, so I can use Avogadro's to go from molecules to moles, and then I can go from moles to grams. This one, it is important to know the chemical formula because each chemical formula has a different molar mass. Carbon dioxide's molar mass is 1 carbon and 2 oxygens make us have carbon dioxide. And I look on the periodic table, carbon is 12.01, oxygen is 16.01. 1 times 12.01 plus 2 times 16.00 is going to give me 44.01 grams per mole. Now, how do I use that as a unit conversion? Grams per mole can be separated out to 2 things. 44.01 grams equals 1 mole. So this is your molar mass unit conversion to convert from one set of units to another. And make sure the grams has the number sign. The mole is 1. The grams are those weighted sums from the periodic table. On the periodic table, carbon's 12.01, oxygen 16.00. Notice I just left it to 2 decimal places because typically, at least in years past, the Virginia SOL is always rounded to 2 decimal places. All right. Now that we know all of our base stuff, we now got to set up our equation. We have 2 arrows, so we have 2 from 2's. The known 10.0 times 10 to the 24th molecules of carbon dioxide. We're going from molecules to moles. 6.02 times 10 to the 23rd molecules equals 1 mole. If we stopped right here, molecules would cancel and we'd end up with moles. So that's why you only would have divided by Avogadro's to get from molecules of carbon dioxide to moles of carbon dioxide. But in this case, they wanted us to go further. So we now have to get rid of those moles. So we're going to go from moles to grams on this last conversion so that we can cancel out the moles. 1 mole is 44.01 grams because we're dealing with carbon dioxide. Again, plug it into your calculator to make sure you're on the right track. It should have the same start as before. Why? Because the other ones we're going from molecules to moles or atoms to moles if it was an element. So the start is going to look the same specifically so you can start seeing these relationships. Okay. If we stopped at this point, before we added in the molar mass, we'd have 16.6 moles, same as before, because at this point, it does not matter what the gas is. It does not matter what the molecule is, as long as it's molecules, you would take 10.0 times 10 to the 24th molecules of a covalent substance is always going to be equal to 16.6 moles of that substance. And then we continue on and we take the moles times 44.01, and that is going to give us 731 grams of carbon dioxide when we round to 3 sig figs. Why 3? 1, 2, 3, same as each other time. When you are setting up these equations, make sure you're setting them up with the entire item all in one chain. Now, if you struggle with math, there are going to be most of the problems on the SOL. You're not going to have to identify which part is which. So you can just go directly off of that mole conversion sheet memorized in your brain. That mole conversion sheet does not show up on the SOL. You have to have that memorized if you have to do it in steps or use the bow tie method. But I recommend practicing it this way because they can give you a problem where they leave it blank. So they could have given you this as 10.0 times 10 to the 24th molecules of carbon dioxide over 1 times 1 mole over 6.02 times 10 to the 23rd molecules times question mark over 1 mole, and said, what goes there? Knowing how to set up this process would help you out. It's the last unit conversion note, so it's going to have to deal with mass, so it's going to be the molar mass, 44.01. But what's going to help you out is if you set it up and learn to set it up each time so that you can confirm, yes, it's grams. It'll be 44.01 grams, or the molar mass of carbon dioxide on the numerator. All right, how many atoms in 3.1 liters of oxygen gas? This one's designed to trick you. Oxygen gas is a diatomic molecule. It's a 2-atom molecule, diatomic molecule. That means it's still a molecule. So you cannot go directly from moles to atoms in this case. So what are we going to do? Start back so you don't get confused. 3.1 liters of oxygen gas is equal to how many atoms? Set up your known and your unknown so that you can go through each step. Liters can go to moles if it's a gas at STP, it is. Moles can go to particles, but this is a molecule. So moles is going to go to molecules in this case, and then we can go to atoms. But our start point always has to be our known, and our endpoint has to be our unknown. We just got to make sure we fill in the right things. We're going to have 3 unit conversions here. We start with known over 1, and then our first arrow goes from liters to moles, from liters on the bottom to moles on the top. Our next conversion goes from moles to molecules, from moles to molecules. Our third arrow is our third unit conversion, and it goes from molecules to atoms, from molecules to atoms. Hopefully that dance is getting easier now, so you can keep watching it. If not, sign up for a one-on-one tutoring and get some more help in this area. Our known 3.1 liters of oxygen gas. That's how we're going to start. This first unit conversion is liters and moles. 22.4 liters equals 1 mole for gases at STP. The 1 goes with the moles, the 22.4 goes with the liters. Next conversion is talking about moles and molecules. We're going to use Avogadro's here. 1 mole is equal to 6.02 times 10 to the 23rd particles. In this case, our particles are molecules. 1 goes with the mole, 6.02 times 10 to the 23rd goes with the molecules. Lastly, we're going to go from molecules to atoms. From molecules to atoms. What do I need to know? I need to know what it looks like. There is 2 atoms in oxygen gas. There's 2 atoms in a 1 mole of oxygen gas. I use the chemical formula here, O2. So this thing is the same thing that we would do if we were going from liters to molecules or liters to particles, except it has that one additional step. I'm going to warn you, this problem comes up only like once in a whole long time. So if you're getting confused on how to use those base units, just always do liters to particles. Don't see moles at the start, don't see moles at the end. Put the moles in the middle and then hope that you have the correct particles at the end, because it's only going to be maybe one question that's this higher level. But for those of you that want the maximum, this can show up. So when we do this, man, there's so much information. Let's cancel liters, moles, molecules, I'm end with atoms. That was my unknown. Phew. Let's rewrite that equation for those of you struggling to figure out what it looks like. 3.1 over 1 times 1 over 22.4 times 6.02 times 10 to the 23rd over 1 times 2 over 1. This is what you would then type into your calculator. So it is pretty long and involved, but it's broken down. You're not going to put the liters or the chemical formulas into your calculator. And what do I get? My answer I get is 1.66625 e to the 23. Now just remember that's 1.66625 times 10 to the 23rd atoms of oxygen. Okay, so it's actually atoms of just simply oxygen in this case, because it's not the molecule. Substitute, solve, sig figs. 1, 2 sig figs, 1, 2. Rounding to the nearest tenth again. 1.6 times 10 to the 23rd if we round down. 1.6, 1.7. If we round up, the last underline is what gets the rounding. And I look next, it's a 6. So we're going to round up to 1.7 times 10 to the 23rd. And that's actually the atoms of just the oxygen part in there. Okay, now what if we're not at STP? This is actually a different standard, but sometimes they throw these problems in here at an odd place. So I wanted to make sure we went through it. This is when you'd use the ideal gas law, PV equals nRT. This only works for ideal gases, but not STP. It will work at STP, but it'll also work at any other temperature and any other pressure. So let's organize. What is the volume? So our unknown is the volume. So I'm going to put a question mark right here. The volume's always going to be in liters in the ideal gas law of 1.3 moles. Moles is N. So 1.3 moles is one of our knowns. At 2.0 atmospheres, 2.0 atmospheres, the pressures in atmospheres, and 300 K. That's 300 Kelvin. That is our temperature. The temperatures have to be in Kelvin. How do I know what these units have to be? Because of our R number. This is called a gas constant. Okay, it's an unchanging number just to help us relate pressure and volume to moles and temperature. It has units liters, so the volume has to be in liters. It has units atmospheres, so the pressure has to be in atmosphere. It has units moles, so the N has to be in moles, which that one always is. And it has its temperature in Kelvin, so the temperature has to be in Kelvin. That's how you know how to use that. That's that unit analysis portion. You can use that to help figure out what units you should have substances in. So what's my equation? PV equals nRT. And instead of sure, I'm going to put in 2.0 because atmospheres is units of pressure. Instead of volume, I'm going to keep that V because that's our variable. Instead of N, I'm going to put the moles, 1.3. Instead of R, I'm going to put 0.082. And instead of temperature, I'm going to put 300. 2 times V is what's on the left. 1.3 times 0.082 times 300 is what's on the right. 2V on the left, combined terms on the right, 1.3 times 0.082 times 300 gives me 31.98. Do not round at this point, only round after you get the whole problem solved. So we got to get volume by himself. He's connected by multiplication, so we got to divide. What we do to one side, we got to do to the other. My volume is 15.99. What's my units? Liters. The volume is always in liters. Substitute, solve, sig figs. This one's different than the others. We had more knowns, so we couldn't use knowns equals question mark unknown. We needed to use an equation to relate things. So we got to look at all of the knowns. 2.0, 2 sig figs. 1.3, 2 sig figs. 300, this one does not have a decimal, so those guys are not significant. It's not 3 Kelvin as your temperature, it's still 300, but 1 sig fig. Up here, 2.0 had the decimal, so that makes that 0 important. That's the difference between those. All right, so we have 2 sig figs, 2 sig figs, 1 sig fig. We round to the least, which is 1 sig fig. So I underline the first significant number. That is going to be round to the nearest tens. Okay, so we're either going to round down to the nearest 10 or round up to the nearest 10. Notice I'm not rounding down to 1 or rounding up to 2. I'm rounding down to 10, rounding up to 20 because we're rounding to the nearest 10. How do I know? I look next. It's a 5. That means round up. Our answer is 20 liters. Okay? Only for ideal gases. Notice it didn't tell me what type of gas. As long as it was an ideal gas, which for year one, if they say gas, you are going to every time assume ideal gas. Every time. And you'll learn about more of that in later years. And that is all for today.